In the back? Okay, great. So I have the tough task of breaking away from the popular waveform inversion talks. All right, so we'll change courses here and talk about microseismic monitoring. Over the past 1 year, I somehow got dragged into microseismic monitoring, and I actually blame Farouche there, her picture is in the middle. Her thesis was on monitoring microseismic data. She was actually dealing with noise suppression on surface microseismic data. And over this past year, we have had numerous conversations with Farouche as well as Farhad over there on how we can, what we can do to improve microseismic imaging in general. And this talk is actually a combination of all those conversations we had, and that explains the long title. Before I go into the details, let me just give a brief 101 course on what is microseismicity. With horizontal drilling and the advent of hydraulic fracturing, gas shales or oil shales, maybe in the future, have become really exploitable. And in hydraulic fracturing, this high pressure fluid is pumped into these horizontal wells, which generates fractures, and it might actually reactivate some natural already pre-existing fractures as well. And all these fracturing activities will generate small earthquakes, which are called microseismics, and they are usually recorded in a vertical borehole or nowadays commonly on the surface, using a surface receiver array. And it is important to image these microseisms. We need to find out where these microseisms are coming from, because that is going to tell us where there is fracturing going on. And why do we need to know where there is fracturing going on? Because we need to find out which zone in the reservoir is being stimulated, so that we can later go fracture the places that have not been stimulated. And that's why it's important to image these microseisms. But the conventional thinking is that these microseismic events are actually dots in a box. These are instantaneous in time, and some dots, as shown in the figure here that I borrowed from literature, there are these dots which represent locations or hypercenters of these microseismic sources. And there's usually associated with the size, which corresponds to the magnitude of these microseismic events. However, it is only natural to think that these microseismic events are not just pops or instantaneous events in time. Rather, there is a source signature associated with these events. For example, if there's a slippage on a fracture, then it takes some time for it to slip, and that would be a slip maybe after a few milliseconds. If you have talked to Mark Zobak of Stanford, he thinks that there's a close correlation between production and microseismic tremors. Microseismic tremors are caused by slow slippage along fractures or faults. And these are not just single pops. These are actually a series of pops. It's like tick, 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 tick. It's a series of microseismic events, and it's really difficult to distinguish one from the other. So how do we deal with such microseismic events? So what we are proposing here is that these microseismic events shouldn't be viewed as isolated events. Rather, they are functions of space as well as time. And if we are able to image these microseismic events in space as well as in time, then that's will give us a better idea about fracture propagation and the time history of fracturing. And in order to do that, we suggest some imaging conditions to obtain this time history of microseismicity or fracturing. This is a very simple simplistic representation of microseismic data, represented by D here, and it's given by the convolution of the microseismic source signature represented by letter S with the Green's function G. And S, that is the microseismic source signature, that is what we are after. And it is a function of time. And this equation is in the frequency domain, by the way. So this microseismic source signature is simply given by the deconvolution of the data with the Green's function. And in the time domain, this source signature is going to be a function of time. So what we can do, and we actually do, is you obtain the source signature as a function of time for every image point. And that is going to give you this cube in space as well as in time. And that corresponds to history of this microseismicity. So this is actually a deconvolution. And this is the first imaging condition here, is the deconvolution imaging condition. And this equation is actually the stabilized version where epsilon is the stabilization factor. And the star represents complex conjugation. And you can obtain this source signature for the different receivers on the surface or the borehole. And then you just average over them to get an estimation of the source signature or the image at a particular image point. And remember that this imaging condition is applied for each trace independently. For stabilization purposes, we can just get rid of the denominator, which leads us to this 1D cross-correlation imaging condition. And this is actually nothing but reverse time imaging of seismic data, where the data D is convolved with the time reversed Green's function. Again, note that these two imaging conditions are done for each trace independently. And then the source signatures are averaged to obtain a source signature of the microseismicity. It's logical to say that to not only look for coherence in time, but also in space. So these imaging conditions can be modified to look for coherence between the recorded data and the Green's function, not only in time, but also in space. And that's where we modify those imaging conditions for deconvolution as well as cross-correlation, and introduce these imaging conditions that exploit the similarity of the data and the Green's function in time as well as space. Farhad later will also talk about similar idea. And finally, the microseismic data is in the frequency domain can be written as a series of linear equations relating the data with the source signature and the Green's function. And this set of linear equations can be solved in a least squares fashion, as shown by this equation here. And one can obtain the source signature that way as well. Let me show you now an example of the result of all these imaging conditions. This is a simple layer cake model. This is actually derived from well-log from Marcellus shale. The star represents the location of the microseismic event, and the two the triangles actually represent receivers in two vertical wellboats, and we each comprising of 11 receivers. Here I am showing just the cross-correlation, two cross-correlation imaging conditions. On the top is the 1D cross-correlation imaging condition, and on the bottom is the 2D. And here I am again showing only the snapshot in time of the two images. The important point to note here is that the 1D cross-correlation imaging condition can introduce certain spurious events as can be seen here, but the 2D cross-correlation imaging condition, because it exploits the coherence in time as well as space, reduces some of these artifacts. And you can observe the same thing for the deconvolution imaging conditions as well. Let's now look at the images at the microseismic hypocenter for all the 5 imaging conditions, as shown on the right. The red curve represents, all these curves are again functions of time. Okay. The red curve represents the original source signature of the microseismic event, and that is what we would like to recover. Note that the two deconvolution imaging conditions, as expected, have performed quite well in recovering the image, whereas the cross-correlation imaging conditions have not been able to, because we are getting rid of this, the denominator here. So the amplitude is going to be incorrect for the cross-correlation imaging conditions. Let me now switch gears and then talk about another aspect of microseismic monitoring that can help us improve imaging, and that is acquisition. Surface acquisition is becoming more increasingly common in monitoring microseismicity. And that is because it is cheaper to lay these receivers up than dig a borehole and put the receivers there. And also, you can use a large number of, not large number of receivers, you can end up with a large aperture with surface acquisition. And here is commonly used surface seismic array. The blue lines represent these receivers laid out in a star pattern, and this is commonly called frag star. Another common acquisition type is to lay these receivers out in equally spaced on a grid, which is equally spaced in X and Y, for example. If I take one of these lines of receivers, this is what it looks like. So this is a 2D line of receivers evenly spaced on that 2D line. Now if I propagate plane waves from each of these receivers to image the hypocenter in a V of Z velocity model, this is what it looks like. You can see that all these plane waves do intersect at the hypocenter, but they're illuminating the hypocenter unevenly from different directions. There are certain directions which are being prominently imaged, whereas most of the angles are not being imaged properly. Ideally, we would like to image the hypocenter evenly from all angles, from all directions, as shown here. This way, the hypocenter is going to be imaged evenly. Not only that, we are going to obtain a better estimate of the source radiation pattern from such an illumination, rather than from this illumination, because this illumination is probably going to give us a false idea about the source radiation pattern, because only a few angles are being imaged. So we can then use this kind of ideal, which we call ideal illumination, to find the location of the receivers on the surface by projecting these plane waves on the surface using the same V of Z velocity model. And this is what you obtain, which is a 2D array with receivers that are more closely spaced around the epicenter of the microseismic event, and further, and the spacing increases as the offset increases. And here is the comparison of the images obtained from the two surveys. On the left is the image obtained from the conventional 2D array, where the receivers are equally spaced on the 2D line, and on the right is the image obtained from this optimized 2D array. And you can see that this kind of resembles the cartoons that I showed earlier. The conventional array eliminates certain angles preferentially, whereas the optimized array is more evenly spaced in illumination. Designing this 2D array in 2D is a much simpler task, because you just have to divide the polar angle around the hypocenter on a 2D plane evenly, and then you end up with a nice set of receivers. But designing it in 3D is more complicated. This idea of sampling the hypocenter evenly from all directions in 3D is not new. It was has been used by earthquake seismologists Folger and Miller, where they actually use the intersections of latitudes and longitudes to find these points. But intersection of latitudes and longitudes is not going to sample the sphere evenly. So what we propose here is to use a geodesic, which does sample the sphere evenly on all directions. And now each point on this grid, each vertex can be used. So the azimuth and takeoff angle can be computed from each vertex, and they can be projected onto the surface to come up with an optimized 3D acquisition. And this is what the acquisition looks like. So again, the receivers are much tightly bunched around the epicenter of the microseismicity, whereas as you go farther along the offset, they are more sparsely spaced. So to summarize, we have introduced imaging conditions for imaging microseismicity as a function of time and space here. And it is important to do that because microseismicity is most likely not just instantaneous. And also, if we can improve acquisition, that can also lead to better imaging of these microseismic events. With that, I'll take any questions.